Morning, everyone. Thanks for coming to our data systems seminar series today. So first, I want to just talk a bit more about this series. It provides a forum for presentation discussion of important data system issues and topics. If I remember correctly, we cover many interesting topics in the past, such as AIDB, open domain question answering, GraphDB, data integration. And today is our great pleasure to have our speaker, Jennie from Northwestern University, to talk about another important topic in data systems, which is data privacy and security. Jennie's work is highly motivated by empowering people with data. More specifically, she investigates pragmatic, privacy-preserving data analytics, federating databases with over multiple data models, and new approaches with which individuals can explore and understand the data. I really enjoy Jennie's work in building practical data systems such as SMCOL, Shrinkwrap for data privacy and security. I'm really looking forward to her talk. So let's welcome Jennie with some maybe virtual claps.
Thanks, Shing.
Okay. Yeah, Jennie, go ahead.
Yeah, so I'm here today to talk about my work on privacy-preserving querying for data federations. So for that, essentially, this is motivated by the observation that data is often a vast and underutilized resource. So essentially, most of it is stored in private data silos, so with little or no data sharing. And that when we do data sharing, and there's a variety of reasons we do this. Sometimes it's for privacy concerns, sometimes people have regulatory requirements that prevent them from sharing the data, or even IP interests. So because of this, naturally, people hold on to their data. It's valuable. It often concerns individuals, but this leads to fractured data sets where the records about an individual are often stored in multiple disparate silos that don't have data sharing agreements. So my work is motivated by this idea of, can we enable analysts to query the union of multiple private data sets such that we only reveal the aggregate query results? So we want to make it so that private data remains private, but that we can still learn high-level insights about it, even if it's spread over multiple data silos. And I'm looking at this question in the context of relational databases with SQL analytics. So to ground this in an example, say that we're doing clinical research over electronic health records. So if a group of hospitals want to pair their electronic health records over for clinical research, then each site remains responsible for protecting the confidentiality of its records. So they have HIPAA requirements in the US. They are not allowed to share raw patient records, but right now, if they wanted to be able to pool their data, they would use an honest broker or trusted third party. And with this, say that we wanted to answer, and the honest broker would be used to answer these questions by having everybody upload their data to relevant data to the honest broker, who would then compute the query and return the results to the person who asked the question. So to give an example of this, say we wanted to know the number of distinct patients who are diagnosed with disease X. And because we wanted to know whether we could form a study on disease X about a potential intervention for that. Now, if we did this distinct count over the N hospitals, the way that they would do it now is each one would upload their patient identifiers who were people who were suffering from X. The honest broker would then deduplicate this and count up the unique patient IDs and then return the count to the analyst or the person asking the question. But relying on this honest broker, just to preview a little bit, is challenging because they could be compromised because they're human. There's so many also intermediate steps that can go wrong in just transferring the data and so on. So to again walk through the steps, so basically a client would send the query to the honest broker. They send, in a conventional data federation, they send the subquery to the databases. The databases would then send partial results to the honest broker. In this case, their patients who are suffering from X, and then the honest broker sends the aggregated output to the query client. So what could possibly go wrong here? So in order to get started with this for sensitive data, you often need to have these complex legal data use agreements in the United States, and where you figure out what will happen in the event of a data leak, where everybody has to be on the same page. And this already takes a lot of money and time. You often have to have a trusted party at each site to validate that the output of the query from the partial results is still okay for release. And in addition to that, by observing the network traces of the data coming into the honest broker, you can learn things about the secret inputs, like the number of X sufferers that exist at each hospital. The honest broker themselves is a single point of security success, because there's just, again, humans involved. Computers can either get viruses, things get leaked, people lose their laptops or their notes. The same is true for the client. So in practice, this is very challenging, and that's one of the reasons why the data often remains locked up in these silos. So I'm going to use this clinical research example interleaved throughout, because this is actually part of my studies is not just about how to make this practical from a computer science perspective, but also examining the various social and essentially the human interaction pieces that have to happen in order to make this data sharing practical. So because I've been primarily doing this through the lens of clinical research from my collaboration with Northwestern Medicine, which I will get into more later. So to address this, we've been building a private data federation, or PDF. And here our goal is to simulate this completely trustworthy third party that's incorruptible and is that will be able to answer these queries and compute arbitrary SQL statements over the union of the inputs of 2+ private data stores. So in other words, we want to cut out the middleman to enable decentralized private data sharing. But we also want the interface to remain the same as that of a conventional data federation. So we want to make it such that as the user poses their SQL queries, as they get the results, that as much as possible, they don't have to think about the underlying security model, because we automatically take care of them. At the same time, we want this to be efficient, and we need to protect the privacy of the underlying input records. So to think about this pictorially, we basically want to go from this space where the analyst is untrusted and we assume that everything else in our pipeline is secure, to say that the private data federation has just the hospitals in charge of securing their own data, and the honest broker is untrusted as well, if we even need one at all. Okay. Now, in practice, as we're moving this trust boundary, we still do need to often maintain an honest broker, just for regulatory and for accountability reasons. So we're going to keep that in our model for now, even though we may not actually need it from a computer science perspective. So to also talk about additional underlying assumptions in our model. So we say that our queries and our table definitions are public. We have a common data model, meaning that everybody agrees to support the same set of tables. In the hospital, that would be like a medications table, a diagnosis table, and demographics table that says like the gender and race and age of the patients. Each column in the table is public or private. So we say that it's either okay for everyone to see it. If it's public, it might be something like a primary key where it's just an integer that's being incremented all the time, or it might be something that's well known, like if you were doing TPCH, it might be like the region table. There's 5 regions, everybody's got a globe, it's okay. That can be public, right? So to start with, analysts alone view the output of their query. So no additional information is revealed except that which can be deduced from the output of the query. And we will relax this assumption of no collusion between the analysts and the data owners soon. We also assume that the data owners will faithfully execute any cryptographic protocols to secure multi-party computation to which they're assigned to compute. So, but let's also talk about what our goals are here. So we have this space of goals that first we want our results to be as accurate as possible while protecting the privacy of the underlying data. So initially, we will say that we are perfectly accurate, and then we'll talk about different levels of accuracy that we can achieve while having strong privacy guarantees. In addition to that, we want compute privacy. So we want to make it so that when we're evaluating the queries securely, that the information that is revealed, if any information at all is revealed, is either stuff we already know because it's public attributes, or it's going to be things that are okay to reveal because they're noisy or otherwise sufficiently distant from the raw data. So we want data privacy. So we want the outputs of our queries to be imprecise enough that they don't leak information that's unauthorized about the underlying input data. And we also want efficiency. So we want to be able to evaluate our queries fast, and so that these answers are both have high utility as well as completing in an amount of time that they will be actionable for the analysts. But these guarantees by themselves are not Boolean. So you can see at the bottom of the screen that we have a few possible design points in this decision space. And because of this, this leads to interesting trade-offs. There's still no free lunch. So achieving this top picture where we have all of these dimensions is not really, it's not doable in practice just because of fundamental limitations of our design space. Like you can't have data privacy where you have strong guarantees that the database is not vulnerable to reconstruction attacks while having perfect accuracy. But we want to empower users with a decision space in this 4D set of choices. So any questions on that? Okay, great. So our first building block is secure multi-party computation. So secure multi-party computation is a suite of cryptographic protocols that will evaluate a function over the union of private data from multiple mutually distrustful parties. So here, this is where we're essentially creating a computational black box that everybody puts their data into compute, and the data owners work amongst themselves to answer the questions, such as our distinct count query from earlier. Now, they pass these encrypted messages amongst themselves to solve for the answer, and this makes it so that nobody can learn about the secret inputs, and we don't need the honest broker. And to a first approximation, it has two things it does to make it achieve this goal. So the first one is that the data is encrypted throughout. So we have the data, in our case, we're using garbled circuits. So you can visualize this as decompiling the SQL query down to logical gates like AND gates and OR gates. Now, in addition to that, it's oblivious, meaning that the observable traces of the execution are data independent. They don't leak anything about the underlying information by early termination, by branching, or other changes in the control flow of the program. Now, because we're thinking about this in terms of circuits, it is Turing complete. And this is analogous to uploading your data to this trusted third party, but not giving them the key with which to decrypt it, even though we're actually encrypting it and into secret shares and then distributing the shares over the data owners. Now, this is great, but again, there's no free lunch. So MPC is really slow. It's 1000x plus slower than running in the clear, and often much worse than that. Because if you want to be naively oblivious, if you truly want to leak no information, then this means that you have to essentially run in worst case every time, worst case complexities. So you can see how this would add up fast. So SMCQL is our private data federation for computing secure multi-party computation over SQL. So here we generalize data federations to support mutually distrustful data owners. And what that means is that we wanted to, again, push this logic out of the honest broker and down into the data owners and make it so that each of these private data federation data owners only learns at most they don't learn anything initially unless they collude with the analyst. But we wanted to make it such that the analyst could just input an arbitrary SQL query and that we could automatically translate it into secure computation or MPC. And that we reduced the use of MPC because MPC is so expensive, we want to minimize the database operators on which we have to use it for computation. So we create a security type system to minimize our use of MPC for ad hoc SQL queries. And also introduce a set of query rewrite rules with which we can further reduce the data that has to be computed in these heavyweight cryptographic protocols. So let's just see briefly how our query lifecycle changes in this context. So now the client doesn't need a discrete honest broker. Instead, they say, I want to know the answer to my queries. How many patients suffer from disease X? So I send this to the PDF client on her workstation. And then the client translates this into secure computation protocols with which to run the query securely, as well as SQL statements that give the inputs for the program. Then the data owners work amongst themselves to perform secure computation over the records of all their inputs. So again, the data owners learn nothing about the inputs of their peers, and they work together to compute the output of the query. In this case, deduplicating their inputs and providing the secure count. Then each of them sends secret shares of the query output, one per data provider, back to the PDF client. They do this over a secure link like SCPing or SFTPing so that each site cannot observe the secret shares of others. And then the PDF client puts the secret shares together and produces the output of N patients. So why SQL for this? The question I get sometimes is, you're a database person, is it like when you have a hammer, does everything look like a nail? So no, that's not true. There are actually some features of SQL that make secure computation accessible in ways that perhaps it wasn't before. So first off, it's ease of use. So unlike prior efforts where we had either, in order to start using MPC, you either had to learn a domain-specific language, like with Wisteria or OblivVM, or you had to learn a new library like EMP Toolkit. Now you just write in pure SQL. So it's implicit that it unions the data over the multiple sources because we have a common data model, although we could support heterogeneous schemas as well. We also have structured data. So the schema itself gives us hints about the data's distribution without revealing anything about the raw tuples. We have things like integrity constraints, primary keys. Many of our columns will have domain constraints, saying, for example, that a week has 7 days or a year has 12 months. And we can leverage this information to reduce the complexity of our queries. So the structured data gives us more hints about how we can do this efficiently. In addition, because SQL is declarative, we have optimizable query semantics. So this means that we can make decisions about how to run the query efficiently in secure computation, or even try to reorder our operators to avoid secure computation entirely without reducing our security guarantees. So SQL has a lot of features that make it possible for us to both put MPC into the hands of more users, as well as to make this run efficiently without interventions and lots of hand tuning on their part. So I'm going to give a brief background on SQL query processing just as it relates to this. If we wanted to ask a question like how many patients were diagnosed with heart disease and prescribed aspirin each year, we might start with a SQL query like this. And then in SMCQL, we have to parse this into a query tree, which we use Apache Calcite for this. Because it supports many different SQL dialects. So here we say, we take the tables in the from clause, we scan those. Then we look at the where clause, we say, well, we filtered on heart disease and for aspirin. Then we join over the two on the patient ID. So we only select patients who satisfy both those criteria. And then we can group by the year and count. So that's all well and good, but if we're doing this securely, then we need to have, in order to not leak information about the secret inputs, like the selectivity of that filter or how many tuples matched in the join, we have to pad all of our intermediate cardinalities to the worst case. And because to do anything less would result in some form of information leakage that we don't have control over. So this means that simply naively doing SQL over secure computation won't scale. So you can imagine over multiple joins so you add another table, then you get to like n cubed, and then and so forth and so on in terms of our complexity of the outputs, and that this just really gets expensive fast. So also with our aggregates, if we don't want to reveal how many group by bins there are, we have to essentially reveal the worst case and just say that the output of the aggregate is the same as the input size, right? So this is really expensive and it won't scale. So when thinking about this in terms of query planning and optimization in MPC, we usually, when we have query optimizers, we like to make decisions about how to order commutative operators using statistics. And we also want to decide what algorithms to use for those operators, what access paths for if you have indexes and things like that. But here, things like access path selection don't matter as much because the bulk of our cost is in computation itself. So MPC will bottleneck on compute time, which because we are computing each gate by passing encrypted messages amongst the data owners, is actually network bottlenecking. So in addition, this is challenging because the query optimizer needs to be able to make planning decisions that are independent of the private inputs. So we can't leak any information about the contents of each table by say, reordering a join or picking a certain algorithm. So one of the things we're going to look at here is how do we maintain compute privacy while running efficiently? And there are a few tactics that we can use here. So one, we can avoid MPC entirely. So again, you can reorder ops to reduce our reliance on MPC. You can simply do taint analysis and say, well, if I'm not touching any private data, then I don't need to make those intermediate results oblivious. So in addition, you can design efficient algorithms for computing obliviously. So you can say that if you have a more efficient join, and I think that actually some of you are working on that challenge of efficient joins, efficient aggregates, and more, to be able to run more efficiently. In addition, you can leverage hits from the schema information and from public attributes to automatically deduce tighter cardinality bounds. In addition to that, you can simply query less data, sample the data instead of viewing it in its entirety. So there's this decision space of how we can run more efficiently while still providing high utility results. But how do we get there? How do we get from the SQL to the secure computation? So with SMCQL, we did this with a code generator. So we created a bunch of templates for our for SPJ, so select, project, join, and aggregation. And you can see here is an example of a join template. So you have, and this is translating from our SQL statement, which we parse and then we extract all these features from, and then translating it into upliv_VM. So you can see here that the join function takes in a left-hand side and right-hand side relation. So before we compile, we say, well, here's the tuple width of L size for the left size and R size for the right size, and we also know the width of the output schema. And then we just iterate over nested loop join style, each using these two for loops, compare each tuple. We automatically generate filter criteria for the join condition, and then project the output. So you can see that even though this is relatively simple, that there's a lot of work that goes into just breaking down the SQL into these pieces and then automatically translating it into this C-style program. But also doing so in a way where each of these bounded for loops will run to completion, so there's no early termination and there's no leakage of which of these tuple pairs actually pass the filter. So that's how we can naively compute it. But in addition to that, now we need to be able to identify which parts of a proposed query tree have to be done in MPC. So we only want the private data federation to compute securely when it's needed to uphold a privacy policy. So recall that each of our table columns is labeled as either public or private by the stakeholders in the data federation. And here we want to trace the flow of these private attributes as they move through a query tree, because we don't want to just say you have to compute for MPC. You have to compute within MPC when you're computing over private attributes. We also need to make sure that any computation that is on a result that's derived from private attributes also is evaluated securely. So if we wanted to, for example, learn about what are the top K conditions that arise in heart disease sufferers, you can see in this example, if we have a heart disease patient registry, that we can do a filter locally to filter down to the patient IDs that appear in this registry. And that after that, we have to perform the aggregate inside MPC in order to get the count of each condition. Now, you might ask, well, could we do a trick where we do partial aggregation locally, for example? Like every site computes for each diagnosis code the count locally of how many people have have a diagnosis for this condition. And the answer to that is, if you did that, then if you input the number of tuples that is the true output of the partial aggregate here, then it will leak the number of diagnosis codes that exist in your data set and break our full obliviousness guarantees. So that's why we're showing it here as being in MPC. After that, we have to sort the counts in descending order in order to get the top K. So in the SMCQL, the security type system will traverse the tree and identify where are these MPC frontiers, where are these cutoff points. We have to start using secure computation in order to uphold our security guarantees. And And here you can see we do that after the filter.
Jenny, a quick question. Yeah. Regarding the previous slides, do you have to manually decide where MPC have to be applied, or there's a smarter way that automatically decide where the MPC have to come in the query plan?
So we figure automatically when MPC has to be applied by analyzing the attributes upon which each of these operators computes. So essentially, our security type system goes through and it says, well, in the aggregate, for example, we would say that the things that will inform our control flow will be the diagnosis code, right? Because we would have to say, well, which group by bin does each tuple belong to, right? And so that's why we would say that if the diagnosis code is secret, that means that we have to switch to MPC mode. Does that make sense?
Yeah, that makes sense. Thanks.
And then any parent operators after secure operator themselves have to be done in MPC in order to protect the privacy of the outputs of the initial point where we discovered that we had to perform computation over a secure column, over a private column. So really it's about finding the minimal subtree that must be computed securely. So in addition to this, finding the minimal subtree, we also have to identify a set of query rewrite rules. We generalize some optimizations from distributed databases to private data federations. So here we want to further reduce our MPC footprint. Our main emphasis is on reducing the size of the data that we input to MPC. So these query rewrite rules exploit semantic equivalences in the relational model to uphold our strong privacy guarantees, but offer additional speedups. So in this example, you can see that we're looking at a semi-join. So if we're joining on a public attribute, like the patient IDs being public on our medication diagnosis table, we just say that these are the patient IDs, but we don't reveal anything about the contents of their diagnosis or about their medications. We can do a public intersection to identify exactly which patient IDs have to be processed in MPC. And then for the ones that are distinct to each site, we process that locally. And then we take this local in-database processing, and at the end, the client can union it with the output of the MPC processing. And this technique generalizes in a couple ways. So first off, we can do this for partial aggregation, but only for scalar aggregates, like count star without group by. We can also do this for partitioned joins on public attributes. So in addition to identifying the intersection set, we can also say, well, I'm going to break this join down into a bunch of small parallel slices or independent slices, and then compute over each of those slices independently. And that brings down the complexity of our output from n squared to, if you have k slices, it becomes basically k times n over k squared. So it becomes a little bit smaller and more manageable. But briefly, when we look at how each of these pieces comes together, you can see that our query performance gets improved dramatically by first using the security type system to identify that minimal subtree that must be computed in MPC. And then adding the query rewrite rules yields additional speedups. So here we're looking at 3 queries from our colleagues in clinical research. So this is working with Abel Coe and his team at Northwestern Medicine. And we set up these MPC queries over a set of de-identified healthcare records from hospitals around the Chicagoland area. And essentially what we found is that by minimizing our use of MPC, just avoiding our use entirely, that had the biggest bang for its buck. And by doing query rewrite rules, that this helped out a lot for queries that have joins, which is the first two. So with the final one, this is the comorbid condition question that we were looking at earlier, where we were doing the aggregates and we're finding the top K conditions associated with disease. And this produced less speed up just because we couldn't really benefit from our query rewrite rules. So, but really it's better to think of SMCQL as a proof of concept. So here we were exploring how we could automatically translate these queries from SQL to MPC, and how to do this in an ad hoc way. So we open sourced this and made it a robust prototype. So it has, again, using Calcite, Apache Calcite, it supports multiple SQL dialects. It uses JDBC connectors, so it can be adapted to many common database platforms. And as such, it's also been benchmarked on numerous papers just because it's a relatively general platform. But you can see in our goal list from earlier that this really only covers the upper left-hand quadrant. So we've got lots of compute privacy. We've got perfectly precise answers because we're doing secure computation and that's deterministic. But once we're done with the query, like we can't say anything about the long-term privacy of the data or what one could infer from the output of the query. Moreover, it's incredibly slow. Even with all of these query rewrites, we're still limited in that we're running thousands of times slower than we would if we were doing this in the clear. So even after this work, those were the big challenges, that we want to be able to provide end-to-end privacy guarantees, and we want to have our query runtimes be much more efficient in order to make this get into the hands of more domains. So when I say end-to-end data privacy, we see that SMCQL protected its private inputs during query execution. So by participating in secure computation, the data owners learned nothing about the inputs of their peers because the computing was oblivious. But what about after we release the query answer? Then we're subject to attacks from the client deducing the private inputs from repeated querying by perhaps just tweaking their predicate a little at a time in order to learn more and more about the private data. And we also have to worry about the client and the data owner potentially colluding or just being the same person. Like in many of these setups, like in the hospital example, the data owners themselves want to be able to query the data, the union of their data with that of their peers. So like for the doctors who are participating in these healthcare consortiums, like they want to advance their own research. So they actually do want to both be a client and a data owner. So we want to be able to make guarantees about what happens after we release the query answer. Moreover, as we start to apply more and more optimizations, we have to make sure that the ones that we create are going to prevent leakage before query processing by making any query optimization decisions that are independent, that are going to be, if it makes decisions that are dependent on the private inputs, that can leak information as well. So we have to make sure that our query optimizations themselves don't leverage private statistics or any insider information about the underlying data. So we need to make sure that the next generation could control information leakage at every step that is observable, both before, during, and after query processing. So the next building block that we worked with here is differential privacy. So I'm sure that this part is near and dear to your heart, right? Because we've collaborated on this a fair amount. So with differential privacy, we inject precisely calibrated levels of noise into query answers. So we want to be able to protect the privacy of individuals in the data set by making it so that the query answers are sufficiently perturbed that no one learns about the private records of one person in the data set, or they can't deduce those outputs with high probability. So great thing about differential privacy is that it's composable. So for repeated querying, it bounds the information leakage subject to a privacy budget epsilon. So we can use epsilon and divide this privacy budget amongst multiple queries. As long as the budget allocation to each query sums to a value of less than or equal to epsilon, then we have strong guarantees with respect to this privacy budget. In addition, we investigated using computational differential privacy to relax these information theoretic guarantees to support a computationally bounded adversary. So this makes it possible for us to also look at different, to be able to look at this, not just in terms of the query output, but in terms of optimizing the speed of our query execution itself. Now, in our taxonomy here, differential privacy gives us a lot of speed. So it's going to be very fast, and it's going to compute at a speed that's comparable to that of doing it natively in the database. The only thing that's different here from using standard differential privacy is that now, right before we release the answer to the query client, we inject some noise into the results. So it has strong data privacy guarantees. So we know that the amount of privacy is proportional to epsilon, and the accuracy is going to be high. It's going to have high utility, but it's not going to be so high that it reveals the contributions of individuals in the data set. So our next effort was about adding these end-to-end privacy guarantees to the private data federations. So we extended our PDF guarantees to cover the prior knowledge of the data owners with respect to the query answers. So we had to think about that for any data releases that we do, and about the cumulative privacy loss from repeated querying by looking at these composable guarantees of differential privacy. And in addition to that, we had to take into account collusion amongst the data owners and the clients. We want to assume that they're talking with one another. And this is joint work with she and her advisor Ashwin that we did in VLDB 2018. So here we want to reveal information in two places. One, we want to have noisy query answers so that the client still gets useful information, but not information that is so accurate that it reveals enough information to reconstruct the private input records. Now, in addition to that, we want to tackle this cardinality bounds challenge. We want to make it so that we don't always have to have worst case intermediate result sizes for our operators that we compute with an MPC. Now, for the query answer, we want to also noise the answers themselves within secure computation so that we don't reveal, so that the real true answer to the query is revealed to no one. So you can see here that this gets us closer to our goals because now we have compute privacy, strong data privacy, and we've increased our efficiency. So here you can see that we have differentially private query execution has three main pieces. And I'm going to go a little faster because I see that we're running short on time. So we have our computational differential privacy mechanism. And here we want to take those exhaustive intermediate result sizes and we want to pare them down to the true result size plus some noise. We also have an execution cost model with respect to the cost of both computing in plain text as well as an MPC. And we have a budget splitting algorithm for allocating the privacy budget to different intermediate result sizes in our query tree to maximize the gain of using computational differential privacy to reduce our intermediate result sizes. So you can see here that if we were doing a join of two relations, that if we were doing this without Shrinkwrap, if we're doing this in SMCQL, then we would have to have n squared outputs approximately. And most of these are going to be dummies because most joins don't produce n squared output tuples unless you're doing cross product. And what we want to do is we want to get the revealed cardinality to be closer to the real size of the intermediate cardinality, but we have to pad it with enough dummy data so that, again, the user can't deduce secret information about the inputs. So we use a Laplace mechanism to inject enough dummy to know how many dummies to inject at each step, subject to a privacy budget allocation. And then we simply, when we get to an intermediate result, we shrink wrap it. So when we say we shrink wrap it, we first obliviously sort the data on its status of having a dummy tag or not. Then we calculate a one-sided DP noise to say how many dummy tuples to add. And then we create a new DP-sized array and copy the data, the truncated data over to that. So you can see, like, returning to our example from earlier, where we had that explosion of intermediate result cardinalities. If we were doing this with the shrink wrap mechanism, we instead can say that each intermediate result size would be equal to the true size plus this Laplace noise of how many tuples to add. And this Laplace noise is proportional to the privacy budget allocation and the sensitivity of each step, where the sensitivity is how much each tuple can perturb the cardinality. So you can see that this makes it so that we can dramatically reduce the cost of computing these operators and how much noise or how much overhead we have to pay on subsequent query operators. So we use, we created a budget splitting cost model a model that helps us understand how much time it will take to run each operator, as well as the cost of shrink wrapping the intermediate results. And I'm going to gloss over that for now, and suffice to say that we use, we have a constraint solver that we use to allocate the budget over these securely computed operators. And that by doing so over the same query workload, we saw substantial speedups, especially as we add more and more joins, because the joins really disrupting this cascade of, like, going up, this exponential blow up of the size of our intermediate results is where this technology shines. So you can see that by having 4 relations doing 3 joins, that we realize speedups of 35x. So very briefly, I also want to touch on a final building block, which is approximate query processing. So here we can also get massive speedups by sampling the input data, and instead of having to execute over the entire data. And in some cases, like, this will be synergistic with our differential privacy use. Because with approximate query processing, users expect tight accuracy bounds because they know that we're only computing the query over part of the input data. So here we're getting faster runtimes and we're getting estimated query results. Now, by itself, approximate query processing doesn't say anything about compute privacy, and it doesn't really make any strong guarantees about data privacy. So actually, like, differential privacy has much stronger guarantees. So I would, you would imagine that on our taxonomy that DP goes much lower, closer to having full coverage of data. It has full coverage of data privacy subject to the privacy budget, but with approximate query processing, it still has noisy results, but we aren't quantifying the information leakage. So we can't make strong guarantees about privacy. And in this work, we focused on online sampling at the beginning of query processing. So we want to pick a subset of the data, and we want to compute the query securely over that subset and still noise our query results in order to uphold our end-to-end privacy guarantees. And so we did this with a system called SAQE, or Secure Approximate Query Executor. So this was joint work with Shim and with Youngji Park and Xiao Wang. And here you can see that we have our 3 components. We have MPC paired with differential privacy, which we need for end-to-end privacy guarantees. And then we compose differential privacy with approximate query processing, such that the 2 are synergistic in terms of how we noise the results. We're not, like, double counting the noise by saying that on one hand we have noise that's attributable to the sampling error, and on the other hand we have noise that is needed to ensure our privacy guarantees. We want to make sure that we are reusing as much noise as possible between those two sources. And we bring that together with secure multi-party computation by introducing a set of privacy-preserving sampling algorithms. So sampling algorithms that perform with a mix of MPC as well as in the clear to both make sure that none of the data owners learn unauthorized information, but jointly we can have a sample that we can noise successfully at the end with differential privacy. And one of the key results here was that we learned that there's an inflection point where as we sample more and more of the data, the noise that we get from sampling will eventually reach a crossover point where our accuracy goes up, and that means that we have to start adding noise on top of the we have to add more noise on top of that of the fixed cost from sampling. So basically, once we pass that inflection point, it's no longer profitable for us to keep sampling. So we have, at that point, if we sample more, then you could see, once we reach that crossover point, we actually have to add more noise. So that means that the additional sampling, the additional data just makes us run longer, and it doesn't actually increase the accuracy of our results. So that was interesting, because that means that we know that there's a cutoff where it no longer makes sense to sample more of the data. And that we know that we can get very accurate results without additional sampling. So with SAQE, we looked into this efficiency accuracy trade-off, and we saw that compared to our prior efforts, so we have SMCQL, and recall that this doesn't have any strong data privacy guarantees, that the outputs are 100% accurate. So there's no sampling, and you can see that our execution time for this this aggregate query is about 250 seconds. Then with Shrinkwrap, where we are having these noisy intermediate cardinalities, we realize substantial speedups. It knocks it down to about 175 seconds, and we have much tighter accuracy, but it's taking a lot longer. Now with SAQE, we have this additional knob. We can decide what our sampling rate is, and as a consequence, we can make it so that we run a lot faster and have a slightly higher error. But you can see that here, if we're sampling just 10% of our inputs, that we're still getting within almost 5% of the correct answer. So these are still very accurate, high utility answers, but they're running much, much faster, like 5x faster in this case. So, well, 3 to 5x faster. And so you can see that this is going to produce better performance, but it may do so at a cost of reduced accuracy. So this is back to that whole there's no free lunch, and you have to think about this as a space of trade-offs for how fast we want to be able to run, how accurate we want our query answers to be, and how strong we want our privacy guarantees to be. So I also want to briefly touch about it on a pilot that we're doing with clinical research. So we're in the process of starting to pilot secure computation with SQL with our partners in clinical research. So we received IRB approval to deploy MPC in a group of Chicago area hospitals under the Capricorn Clinical Research Network. So the Capricorn Network covers 8 major healthcare institutions and about 200 hospitals and clinics in the Chicagoland area. So this is the first of its kind, to the best of our knowledge, for deploying MPC over healthcare data. So we've spent a lot of time just understanding the needs of what it takes to make MPC practical in these high stakes environments. And so we've just received our approval for deploying the virtual machines, and now we're just getting it out there and starting to prepare to collect results. And we're going to open source the code and the performance results. And again, this is both emphasizing how to make this both efficient and accessible to analysts. So we want to make it so that, in addition to not needing this honest broker anymore, which is a real pain point for many clinical researchers, we want to make sure that we can give them high accuracy on their query results. And also, we're preparing to write a CACM article about this adventure, just because there's a lot that goes into learning about needs finding for bringing MPC into the field. So in conclusion, we saw how private data federations will make it possible to securely share private data at an unprecedented scale. So we found some novel connections between the relational model and oblivious computing with which we can make this technology efficient for analytical workloads. So we say, well, there's all these optimizations from the database world that you can generalize to bring them into this oblivious computing space in order to make MPC run fast. And we've been investigating this multi-dimensional space for optimizing PDF queries, trading off among speed, accuracy, and privacy. And at the same time, we've been open sourcing this technology and piloting it with our partners in medicine to investigate what real world impact we can have. At present, we're also pursuing emergency use authorization to extend our pilot to COVID research. So any questions?
Thanks again, Jenny, for giving this wonderful talk. And yeah, I personally really enjoyed it, even though I know them pretty well, but I still like it. Yeah, thanks again. And thanks everyone who coming to the seminars, and have a great day.